Good day. This video will continue to discuss the STPM passage in 2020, Section B. A heating coil of 1 kilowatt is designed to operate from a power supply of 240 volt at room temperature. The coil is made of nickel wire of diameter 0.5 millimeter. The resistivity are given here, so calculate the length of the nickel wire. So we have the formula of the resistance as rho A over A, but the resistance is not given. Instead, we are given with the power and also the voltage. That we can relate these three variables as the power equal to V squared over R. Hence, we can express the resistance as the V squared over the power equal to rho L over area. And we have all the information given except the length of the wire. So that's what required by the question, that the length will be equal to AV squared over rho P. So we just put in the value and you can get the answer. So area will be equal to pi d squared over 4, so 0.5 millimeter square divided by 4. And then multiply the square of the voltage, 240 square, divided by the resistivity, divided by the power, 1 kilowatt. So equal to 7.54 meter. Okay, the length is equal to 7.54 meter. So move on to B. Explain the effect of temperature increase on the power dissipated by the coil. So we learned that when there's current flow through the coil, so there's a power dissipation as heat energy. So higher temperature increase indicates there is more power dissipated by the coil. And when the temperature of the coil increases, resistance also increases because this is the conductor. Okay, so this also reduces the power dissipation because the power is inversely proportional to the resistance of the coil. So if you relate back what happened in the daily life, that when you heat up a water, the rate of change of the temperature is getting slower when it is close to the boiling point of the water. So that's what happened. So we move on to question 17. A galvanometer of resistance 25 ohm is converted into an ammeter using a shunt of resistance 1 ohm. So ammeter is used to measure the current in the circuit, which consists of a resistor 15 ohm connected in series with a battery of 25 volt. If the internal resistance of the battery is negligible, determine the current measured by the ammeter. So the measurement of the current is not accurate because it has the effect caused by the resistance of the ammeter. So you have learned how to build the ammeter using a galvanometer connect in parallel with a shunt resistor. So this should be the arrangement of the ammeter. And we learn how to use your ammeter in your lab, that it should be connected in series in the circuit. So this should be the imagination that about the circuit in this question. So to determine the current measured by the ammeter, so first we need to obtain the equivalent resistance. So the 25 ohm is in parallel with the shunt resistor, which is 1 ohm. So it will be equal to 25 times 1, 25, divided by 25 plus 1, 26. So this is how you calculate the resistance in parallel, which is equal to 0.96 ohm. And then we can obtain the actual current, the measured current is the voltage, 25 volt, divided by the total resistance in the circuit. So 25 divided by 15.96. So answer will be equal to 1.57 ampere. So this is the current measured by the ammeter. And then we move on, determine the percentage difference between the measured and the actual current. So the actual current should be without the resistance of the ammeter. So we mentioned that the ideal ammeter should have 0 resistance. So to calculate the actual current, we just ignore the resistance of the ammeter. Then we have 25 volt divided by the 15 ohm, which is in the circuit. So it is 25 divided by 15 equal to 1.67 ampere. And to obtain the percentage difference, what we do is we get the difference between the actual current and the measured current, divide by the actual value, 1.67. So this is what you should do. So it is equal to 1.67 multiplied 0.57 is 0.1 divided by 1.67. So it is equal to 5 it's about 6.0%. So move on to question C. So describe the function of shunt in the ammeter. So shunt is a resistor that has a very small resistance connect in parallel with galvanometer. So why? Okay, because this is to divert more current away from galvanometer, so the galvanometer can measure higher value of current at full scale deflection. So we proceed to section C, question 18. Define electric field strength at one point in an electric field. So we have force equal to QE, then the E is equal to F over Q. So we can define as the electrostatic force per unit positive charge in an electric field. Next, we look at B, explain the motion of electron which moves into a uniform electric field in perpendicular or in the same direction as the electric field. So let's answer the first one. So if you move perpendicular direction in the electric field, so probably you can draw a diagram here. So first of all, it will experience a force that is in opposite direction to the electric field. Okay, because this is an electron, so it has a negative charge. So when a Q multiply E, so you would have the negative of force. So the force would be in opposite direction to the electric field. So as shown in the diagram, so what we have is the electron will continue to move in constant velocity in the horizontal component, while accelerate towards the positive plate, or also we can mention about the higher electric potential in the electric field. So as a result, the electron will move in a projectile motion. So for the second case, that it will move in the same direction as the electric field. So you need to be careful with the same direction. So what you can expect is the electron is moving towards the negative plate. Okay, it's same direction as the electric field. So it is moving in the same direction. So what you have is that it will experience a repulsion force. Okay, because the force will be in the opposite direction. So what the electron is doing is it will decelerate until it stops and then move in the opposite direction of the electric field. We move on to the next one. Two equal point charges at A and B with the magnitude of 5 microcoulomb each are located opposite to each other 2 meters from the origin. So determine the magnitude and direction of electric field strength at P, which is located 1 meter below the origin due to the point charges. So the question only mentioned about the magnitude, so we just assume that both of the charges is a positive charge, that the electric field is produced in an upward direction, okay, upward. So from here, maybe you can start to determine the rest. R first, get the distance from A to P. So it is also equal to the distance between B and the P. So we just apply the Pare's theorem and we can obtain the distance as the square root 5 meter, while the angle, you can just apply the trigonometry and you obtain 63.43 degree. So we have the same magnitude of charge and also the same distance, so we could expect the electric field strength due to charge A and B are equal. So we just key in the formula, okay, and then we can obtain the electric field strength in the direction as stated in the diagram. So we have the 5 microcoulomb divided by 4 pi epsilon r squared. Okay, so the r is 5 squared, so divided by 5. And you would have 8,987.6 volt per meter. Okay, so this is the electric field strength. And then we're going to calculate the resultant electric field. So first of all, we're going to split into two components. One is the horizontal and the vertical components. So for horizontal components, quite straightforward because both of the electric field is in opposite directions. So what we have is the electric field due to be in the horizontal component will minus the electric field due to point A. So what we have is equal to 0 because they have the same magnitude. And then in vertical components, both of the electric field is in downward directions. So we just set the downward as a positive value and we're going to obtain the magnitude of the electric field strength in the vertical component that is equal to the electric field multiplied cos 63.43. And they are equal, so multiply by 2. So what you have is 8,040.1 watt per meter. So the resulting electric field strength at P is 8,040.1 watt per meter in downward direction. So we move on to question 19. What is meant by magnetic flux density? So this is definition about the magnetic flux density, which is tested in one of the past year before. So we have two cases to explain about this, which is the moving charge and also the current in the conductor. So for the moving charge, that the B is equal to force over the charge and the velocity. So magnetic flux density is the magnitude of the magnetic force acting on a unit charge which moves at 1 meter per second perpendicular with the magnetic field. For the conductor, we have the force over the current and the length. So it is the magnitude of the magnetic force acting on a unit length of the conductor, which carry a current of 1 ampere perpendicular with the magnetic field. So here you can choose either one to answer this question. So look at the second one. Explain the existence of magnetic force acting on the conductor. So we learned about the magnetic force can be determined by the force equal to the current, multiply the cross product of the length and the magnetic flux density. And the magnetic will be the force equal to ILB multiplied sine theta, where the theta is the angle between the magnetic field and the direction of the current flow. When the conductor carries a current that flows perpendicular with the magnetic field, so we have the angle as 90 degree, which would be the maximum value. So there is a magnetic force acting on the conductor, which is at maximum value, or the force is equal to ILB. Proceed to the next one. A conductor of length L and area A carrying a current I is placed in a uniform magnetic field with magnetic flux density B at angle theta with the magnetic field. Derive an expression for the magnetic force on the conductor. So the derivations can be found from the textbook. So let us do the revision. First of all, we need to have the number of electrons in the conductor, which is equal to the electron density multiply the volume, and we have the length and the area. So it is equal to NaL. And from the syllabus, you only require to remember the formula of the force on the charge, which is equal to QVB. So the force on one electron is equal to EVB. So to obtain the magnetic force on the conductor, it is the magnetic force or the total force on the n electron in the conductor. So what we have is the force equal to the n multiplied F, and we substitute all the expression above. So we would have NaL EVB. And when you rearrange the equations, you can obtain NAVE, which can be substituted as the current ILB. So this is what has been taught in the textbook. And from the question, we have another variable, which is the angle. So what we have is just add the angle in the formula of the force, which is equal to EVB sine theta. And then we just copy in all the sine theta in the following equations. So that is the final expression of the magnetic force on the conductor. So we move on to the next question. An electron is accelerated through a potential difference of 2500 watt and then enters a region which has a uniform magnetic field of 0.25 Tesla. Determine the maximum radius of the electron path in the magnetic field. So you can imagine that there are two cases here. First is the electron gaining the kinetic energy through a potential difference, which is the electrical potential energy. So this is something that you have learned in the topic of the electrostatic force, or to be more specific, is the production of the cathode ray, which has been discussed in one of my videos before. So what we could expect is the electrical potential energy U equal to QV is going to be converted into the kinetic energy of the electron. And then the second case is when the electron enter the magnetic field. So we know that there will be a magnetic force that is perpendicular to the motion of the electron, which will become the centripetal force that causes the electron to move in a circular path. So what we have is the magnetic force on the charge is a QVB is equal to the centripetal force mv squared over r. So if we rearrange the equations to obtain the expression of the radius, then the r will be equal to NV over QV. So we have the mass, the charge, and the flux density, but we don't have the velocity of the electron. So we need to solve the first equations to obtain the value of the velocity. That from here we can obtain the expression of the velocity as the square root of 2 QV over the mass. And now we're going to key in all the value and we can obtain the velocity. So it is equal to the 2 multiply the charge of the electron, multiply the voltage 2500, divide by the mass of the electron. And then we square root the answer. So you will obtain that it is equal to 2.97 times 10 to the power of 7. So 2.97 times 10 to the power of 7 meter per second. And then we're going to key in the value in the second equations. Then you can obtain the value of the radius. So it is equal to the velocity multiply the mass of the electron divided by the charge of the electron divided by the flux density, which is 0.25 Tesla. In the end, you will obtain that the radius is 6.74 times 10 to the power of -4 meter. So this is how we can solve this question. We proceed to question 20. State the Faraday's law and Lenz law, so something you can obtain from the textbook. So let's skip the question and proceed to question B. Metal rod PQ of length L is moving at constant velocity across a uniform magnetic field B on the frictionless conducting rails which are connected by a resistor R as shown in the diagram. Explain why a force is required to move the rod at constant velocity. So let's read through the answer. So we learned that when the metal rod is moving at constant velocity to the right, there is change in magnetic flux that based on Faraday's law, we have the induced current flowing in the conductor. So if you apply the Fleming right-hand rule, you should obtain that the current is flowing from the Q to P. Okay, based on the Fleming right-hand rule, current is flowing from point Q to P. So after that, when there's a current in the conductor, so there is a magnetic force acting on the conductor, which is to the left based on the Fleming left-hand rule. So overall, the process is quite simple that when you move, you have the change in magnetic flux, so you have the induced current. But when you have the induced current, you have a magnetic force that is acted to the left. So this is why a force is required to cancel the magnetic force, which you apply the force to the right to cancel the magnetic force so that the rod can continue to move at a constant velocity. Proceed to the next one. So derive an expression for the force by using the laws of electromagnetic induction, which is referred to the law of the Faraday and also the Lenz. So what we have is E equal to dV dt equal to negative B multiplied the dA dt. So the motion of the conductor involves the change of the area. So and then the direction of the induced EMF is given in the textbook that we have the E is equal to negative BL dx dt, where the rate of change of the time is the velocity of the conductor. But now what we're going to do is to derive the expression of the force on the conductor. So based on the conservation of the energy, that we're going to apply a force on the conductor so that it can continue to move in a constant velocity. So when you apply the force on the rod to move through a certain distance, that is what it means by work done on the conductor. So which is converted into the electrical energy in the conductor, which is the induced current in the conductor. So what we have is the work done on the conductor is the force multiplied the distance traveled is equal to the electrical energy that we have the current in the conductor, VIT. So here the voltage here will be referred to the induced voltage, which is equal to BLV. And then we're going to put into the expression that we have the BLV multiply IT. And then you can move the time to the left that we have X over T is equal to the velocity, which is equal to VLVI. So you can cancel the velocity, and in the end, you can obtain a very family equation that is equal to ILV. So that's how you can derive the force. So proceed to the third questions. Determine the mechanical power to move the rod at constant speed of 5 meters per second if the length is 1.2, R is 10 ohm, and the magnetic flux is 2 Tesla. So if you check all the values given that you have the speed, you have the L, and you have the B, which is BLB, which is the formula of the induced EMF. So if you want to determine the mechanical power, so I suggest you can use the formula of the electrical power because the mechanical power is equal to the electrical power based on the conservation of the energy. So what we have is the power is equal to V squared over R as the formula of the electrical power. So the V here will be the induced EMF, which is the BLV of square over the resistance. So all the values here are referring to this formula. So just key in the value and you should obtain the value of the mechanical power. So first of all, we obtain the value of the induced EMF, which is the magnetic flux density 2, multiply the length 1.2 meter, multiply the velocity, which is 5 meter per second. And then we square the answer. So divide by the resistance 10 ohm, and this should be the mechanical power 14.4 watt. So that's all for the discussion. If you still have any questions, you can leave it in the comment section, or you can post your question in the Telegram group. So that's all for today, and thank you for watching.